I had a real issue, so I just had to One, two, three, four. How am I doing today? I also speak. Let's just by hearing this. So that's just by having these small piece of code here. And let me show you another example. If I go back to the, if I reload this one here. Sorry? Yes, that's right. Yes, that's right. So it's a way that you can quickly test some ideas. So this was the original code we had before. We also it also allows you to add your own cards. So you know, with Gunn has talked a lot about cards and tapping and swiping to different menus, things like this one. So I can go down now and I can comment out different parts. So I go to here and I can comment this part here, and go down to this part here, and uncomment this part here, and this part here. So now this one, I made a mistake. I should comment here. So this just has a small line for cards. So this, you see, it has it says tree add. So you add this one here, and then this one. So these are two cards. One here, one here. This card here also has some children as well. So when it runs it, you'll see a timeline with two cards. But when you tap on the second card, it will open up two children cards also. So, you know, if you were to do this in Java, it may take many lines of code, but JavaScript are very simple, so just prototyping tools. The disadvantage, though, is that you have to connect back to their server to run the application. So if you wanted to build an application that you wanted to show at a conference or somewhere, and you did not have connectivity back to the server, then it would not work anymore. Because so that's a disadvantage. But the advantage is that it's very, very quick and easy. So you could use this one to prototype some ideas, and when it's working nice, then you could then rebuild those application in Java or something like this one. So let me see this one running as well. So let's just go back to the. So here we're back on the playground again, and then if I run this project. So if I tap here, you see now there is one card says body text, second card says body text as well. And then if I tap on this one, it will open up child. One card says child, two cards says child there as well. And you know, I can add more as well. Let me just get rid of this one here. So we could add another child here, and another one. Okay, so now we have 4 children. And so now if I run it, oops, let's go back to the, so now you see there's 2 cards again still. If I tap on here, now I have 4 cards. Hey, Canal, how are you? So it's a very fast way for prototyping, and then, as I said, there's a lot of other support as well. So, for example, there's some sensors here showing nothing. Huh? Should be some. That's interesting. Okay. Not sure why it should be showing some. There's some, okay, some window there. Then when I hit this one, I don't know. There should be some text there, but it's not showing it. But anyway, so hopefully they give you some idea a little bit more about what you can do with WeScript. So it's just another way to prototype for glass applications as well. So let me take off the display here. So what I wanted to talk about today a bit more was about some of the technology for user interfaces, and then we're going to talk about some directions for research. Okay. So we started yesterday talking about the different displays and different display types, like the different types of head-mount displays and see-through display. Did you try yesterday the BT100 display from Epson? The see-through one? Okay. So we've got one of these on order. It has not come yet, but this is the 200. And the good thing about this one is it has a much higher resolution, 960 by 540 pixels. So about 1.5 times the resolution of Google Glass. And also completely see-through. And the field of view is a little bit bigger, 23 degrees rather than 15 degrees. And then I think Gunnar also showed you the music one as well, yes. Okay, great. So what I want to talk today a little bit more is about some input technologies and some other methods for building wearable applications. So of course with wearable computer you cannot use the mouse and keyboard for input or anymore because you don't have those devices. So, but there's a variety of different input devices that you can have. So you could use some natural input like speech and gesture, or some physiological measures like heart rate or something as well. One of the popular means of input is using chording keypad. Like this one here is called a twiddler, and this one allows you to use multiple fingers at the same time to input for each individual key. So on the keypad here, there is just 12 keys, but if you push them together, you can type quite fast. And so people have shown that if you use this one, you can get between 40 and 60 words per minute after you've been practicing for about 30 hours. So it's almost the same speed as typing with a normal keyboard. And it's much faster than using, for example, multi-tap keyboard key input on mobile phone. So if you have a T9 phone where you've got to push each button that number of times for a letter, this one you get maybe 20 words per minute. So this graph here shows the number of words per minute after how many hours as people type more and more text. So you can see here they've done 10,000 sentences, and now the words per minute is approaching 60 on average, but some as high as 70 and some as low as 30. So this is a very popular input device. Some people think that it would be very nice to have virtual keypad floating in the air. So so you could have keys here, and you can be pushing them with your finger, like this one. It turns out that is not as good as people will think. So for input, the challenge is that you cannot feel anything. So when you're typing on a normal keyboard, you can feel the keys, or when you're pushing with QWERTY keyboard. So that means that your input rate is a bit lower. So there was a study done early this year showing that when you use the floating QWERTY keypad, like this one here, then you can type up to about 20 words per minute. You also get tired as well if you're doing this one all the time. It's a little bit tiring. And I think some of you may know the swipe keyboard input from Android, where you swipe very fast. So they also implemented this one, and they had some automatic word completion. So as you're swiping, then you can select the word when it's completed. And this one got up to about 45, 47 words per minute. So it's faster, but still not as fast as a real keyboard, 60 words per minute. And with handwriting, around 20 to 30 words per minute. Some people have been doing research on unobtrusive devices. So Jun Rekimoto is working on this one. And the idea of this one was to use capacitive sensing. So if you have a capacitor wrapped around your wrist, so you can see the capacitive plates, this is cross-section of the wrist here, then as you start making hand gestures, the muscles in your wrist change, and it changes the capacitive sensing. So you can have, so you can make different shapes, and it will change the capacitive sensing reading, and so by that you can detect different hand shapes. So this could be one way of having input with your hand without having to touch the glass device. People have also done some work with, the same person did some work with touchpads on clothing. So you could imagine that you have some clothing, and in the clothing you put a metal plate or conductive plate, and then you have a transmitter on your wrist that is transmitting a small amount of current. And then when you touch the parts of the clothing, it will detect the touch by again capacitive sensing. And so you could use this to make interactive clothing. So if you touch different parts of the clothing, it would mean different things as well. And then Desni Tan from Microsoft was doing work on the EMG. So this is electromyography, and this can also be used to detect muscle activity. So he had a very nice project called SkinPut, where you would project onto your arm and make it like a menu on your arm, and then you could touch different parts of your arm and detect the touch as well. Let me show you a video of this one working. And this is a project done at Microsoft 3 years ago. Let's see here. Okay.
Using the Photon Tunland Field
Have to watch the ad first of all, sorry.
Loaded with features and powered by the legendary
Okay.
In this video, we present SkinPut, a bioacoustic sensing technique that allows the body to be appropriated as an input surface. When a finger taps the skin, the impact creates an ensemble of useful acoustic signals. When slowed down 14 times, we can see transverse waves on the skin's surface. However, complex longitudinal waveforms also propagate through the body. To capture these signals, we developed a special-purpose bioacoustic sensing array. Variations in bone density, size, and mass, as well as filtering effects from soft tissues and joints, mean different locations are acoustically distinct. Software we developed listens for impacts and classifies them. Different interactive capabilities can be bound to different locations. Here we see a user playing a game of Tetris using their fingers as a control pad. In our prototype system, we chose to focus on input for the arms and hands, and developed the armband for sensing. In our user study, we evaluated several input location sets, which demonstrated our approach could achieve accuracies as high as 95.5% for 5 locations, a sufficient number of buttons for many mobile interactions. Segmenting purposeful input from false positives is robust and remains functional while walking and jogging. Many uses are possible. Consider, for example, an audio player strapped to the arm, which could be controlled by taps to one's fingers. It is also possible to incorporate a pico projector into the armband already situated on the upper arm. This allows for not only sensing, but also projection of a dynamic graphical interface. Here, the system renders a series of buttons on the wearer's forearm. Users can simply click the desired function with their finger. This interface is hierarchical, allowing the user to access a wide range of potential functionality. As you can see, finger inputs are segmented and classified in real time. Alternatively, we developed a scrolling-based interface. Here, the user taps on the top or bottom of their forearm to slide the selection up or down one item respectively.
Yes, you see, it could be very interesting to use. I think it was a bit dark in the video, but one part showed having phone keypad, and you could push different numbers on the phone here, and then you could call the person. So it's a very interesting method for input. Though you have to calibrate carefully for each person, because they were saying there that different people have different density of bone, and some people have thinner arms and other people, or longer arms, so all those factors change the propagation of the waves that they're tracking. So there are some things to consider though. First of all, you have this gorilla arm technique. So if you have your arms always in space like this one, it can be very tiring as well, because you have to hold the arm up all the time. Also comfort, so people want to do very small gestures normally by their waist. And then you have to think about interaction on the go. Can you input be done while you are moving? So there was a study done to show, there's a very famous, in interface studies, there's a very famous law called Fitts law. Do you know Fitts law? So Fitts law is it's a law that basically tells you how long it takes you to select objects. So if you have on the computer screen a very big square, and you have to move a mouse from one location to tap on the big square, then it's very easy because it's a very big square. Then as you make the square smaller, 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 then the time it takes to tap increases because the square is harder. So if you have a small icon on desktop, it takes more time to select than a big icon on desktop. So this is what Fitts law is. It basically says as the size of the object decreases, it takes longer to select. But they also found that Fitts law still applies when you're walking and interacting as well. So as you start walking around and you want to try and input, then the speed of input goes down. So for example, yesterday I was walking around the campus and I was following beside a woman, and she was texting while she was walking. But she was walking very slow because she was texting. So they say that if you're tapping while you're walking, it can reduce your speed by more than 35%. And of course it increases the errors as well. So you have to think about how that will impact as you're walking on the go too. So I want to talk a little bit about some interface metaphors. So with once you've thought about the input devices, then you can think about what interface metaphor you're going to apply to the user. And with Google Glass, of course, they have this timeline metaphor we showed already, where you're swiping and you see the clocking. But there could be other metaphors you could apply as well. So one interesting metaphor that we've been looking at is different ways you can do information display. So you could imagine when you were in Google Glass, in most cases, it does not matter where you're looking, you see the same information. So if I'm looking at the clock, I turn my head around, it's still showing the same information. So this is something that we would call a head-stabilized view. So the information is fixed on the head, and wherever you look, you're seeing the same information. But you could have other types of views as well. So another variation of this is body stabilized. So body stabilized is where you have information around you in a kind of virtual sphere. But and as you turn your head around, the physical display is turning, and you're seeing different types of information coming into view. And then if you're doing augmented reality, and with augmented reality you want to see some virtual content fixed to the real world, then this one was what we would call world stabilized. So, for example, if you're doing brain surgery and you want to see virtual information superimposed onto the real brain, then you want to make sure that the information is stuck on the real brain, because if you're showing where to cut or probe. So for each of these, they require some type of tracking. So with the head stabilized, because the view is not changing where you're looking, this was no tracking. For the body stabilized, we want to track your head orientation, so 3 degree of freedom. And then for world stabilized, we need to track the orientation and also the position. So as I move around, getting closer, further, the brain information is staying fixed all the time. And we've done some studies showing that if you use spatial cues for wearable information, then you can help people to find information faster. So for example, in this case, you could imagine if you had this interface here, and you had maybe 8 or 10 virtual screens around you. And as I turn my head one way or other, I would see different screens. I might need to search for information. And one way of displaying it would be to have, with head stabilized, you could have all of the screens on top of each other. So as I'm tapping, it would show a new screen each time, going through cycle. But with body stabilized, I could have screen here, and as I turn my head, I would see different screens as well. So we did a study where we compared the performance in finding specific information. So you see here is a screen, and on the top right-hand corner in the green blue square, there's a symbol spade. So the goal was to cycle through the screens until you found the screen with the same symbol, and then tap when you found it. And we found that if you had a spatial interface like this one, you could use some spatial cues to help you. So for example, you could use spatial audio. So in one ear you could hear more loudly in the other ear if the screen was on the right side. Or you could use visual cues. You could have an arrow pointing saying turn your head this way, and it would turn around. So when people did that, we found that they could find information about 30% faster than in the head stabilized way. People are very good at mapping spatial information onto into their head. We also did a similar project with audio conferencing. So if some of you have been on an audio conference and there have been 3 or 4 people on the other end of the phone line, if those people start speaking at the same time, you cannot hear them because everybody's voice comes through one speaker. But what you can do is you can take those same people and you can spread them around you in a conference space, and then when they're speaking you can spatialize their voice, so different voices come from different locations. And we did that one, and we could find that people could very easily distinguish different types of speakers, but because they can use a location. And then you could combine these together in a halo display. So in this case, you could imagine that you could have different types of information at fixed locations relative to your body. So for example, if you want to access your phone, maybe there's a virtual phone that's kind of stuck here. So if I put my hand up to here, then it would select the phone, and I would see the phone selection as well. So there's a lot of different ways that you could use spatial or interface metaphors to help with interacting with wearables in a new way. I think I've already talked a little bit about the attention, haven't I? Did I tell you this before? But yeah, I think I talked already about this one. So, but just to re-emphasize, so spatial, the nomadic radio was an interface that used spatial audio cues. So you had, in this case, there was no visual display, but they had 2 speakers on your shoulder here, and the speakers would play spatial audio. And if you got and they had also a voice recognition around the microphone here. So if you got a audio message, like somebody gave you a voice message, then it would appear around different parts around your head depending on the time of day that the message came. So if it was at 12 o'clock, it comes in front. If it appeared on at 2:30, it appears off to the side. And then they would use those same things to provide different types of notifications and then layer those information as well. And in fact, there's a new class. Let me show you a picture. So people are now thinking about how you can build wearable technologies that don't have any displays, and they call them hearable interfaces, not wearable interfaces. So you'll see here, is there a picture? Okay, I have to show again. So they've been looking at how you can build, if I go back to the pictures, very small, here we go, devices that can fit into your ear, and then they would, here we go, they would also provide spatial audio and quite rich interaction experience. So if I'll play the video here, and you'll see what they have is two small headphones that fit in the ear, and they have, it does not show the picture here, they have, I'll click on this picture, go here, sensors in the ear to sense touch and other things as well. So you can see here's different types of sensors. So if it's in the ear, you can have some medical sensors, so they can use pulse oximetry, so they can detect in your ear the oxygen level of your blood, also the heart rate, and then they have some accelerometer, a microphone, and they have wireless controller, so you just have to move your hand around your ear and it will detect it. And then some 4 gigabytes of storage, so quite a lot of space, but it's all sitting inside your ear. So let me play the video and you can see working here. You can play music if you want to. It's water resistant.
Come on, faster! Go, go, go! Woo!
So this is called the Dash, and it's available for pre-order, but I'm not sure how long before they deliver. But they're selling for $300, and as you can see, it's all these has all these sensors in it, a headset, display, and so forth. So this is, I think, people will also start exploring with devices like this how to be able to provide it just audio-only wearable experience as well. Okay. So I want to talk a little bit about some perceptual issues. So if you're building a glass experience, then of course you are showing information over the field of view, over the person's eye, and so then there are some perceptual issues there as well. So there can be some issues related to the environment itself, related to capturing the environment, augmentation, display devices, and also with the user too. There's kind of three main areas of categories of issues. One is information presentation. So how you can, these are cognitive issues, so how you can display information in the real world. The second is physical interaction, so how can people manipulate the content they're showing. And then there's cognitive issues around creating a shared experience and building collaboration in that sense as well. With the augmented reality, then what you're trying to create is a strong sense of depth. So you want to be able to show where the information is. And there are a number of ways that you can do that. So if you have two displays, people will typically use binocular disparity to show depth. So they will have two different eye images, and they show where the content is by the eye images as well. But you can also use visual cues like occlusion and things like this one. So the objects that are further away will block objects. They will be blocked by objects that are close as well. So when you're dealing with depth, you can use different depth cues here, like icon size, overlapping objects, shadows as well. And you have to also think about information presentation with the visual clutter that you're trying to present as well, and how you want to present information to the person. So, for example, people had some idea that they would make an application where you could use take Twitter information and show it geolocated around you. So as you start getting Twitter tweets, instead of just seeing it on your phone, you will see it in the real world around you as well. And that sounds like a very good idea until you realize that there are many, many tweet messages coming, and your interface could be very cluttered. So you could imagine here is kind of AR interface, and maybe you get one Twitter message here, but then you start getting more, and before you know it, your whole screen is full up with Twitter messages. So one of the important aspects of designing wearable interfaces is how do you filter out the information and just show what is most relevant. So this is typically how you would do that. So you can see here you have the person's display, and you can imagine that there is a lot of data out in the world. So there's large amounts of information about who is around you, what virtual content there is being shown, and so forth. But that information is not all interesting for me. I'm only interested in certain pieces of information. So what you can do is you can take the user information up the top. So the user has some sort of context, something they're interested in. You have some information about their location, so from GPS, and also head pose, so where they're looking. So this tells you where the person is, what they're interested in, where they're looking. And you can use this to filter the information. So you have all the world's data, you filter it down to the information that you think they are interested in. And then you can do some user interface planning. So which information do you think needs to be shown on the screen at any one time? And then you can do some view management to show the right information, and then you show it onto the screen. So this is very important because it can help improve the task. So this shows, for example, an augmented reality interface from the US military. So the US military developed some application so they can, when somebody fires a gunshot, they can use microphones to locate where the bullet was fired from. So they might want to then use that information to tell you how to get into a building behind the person that is shooting at you. So here's an example of an interface for that. So here's the AR interface, shows you all the buildings, and it shows you on here where there is somebody has fired a gun at you. But you can see on the left-hand side it's very cluttered. So there's a lot of information here that, like in the background, that you may not need. But on the right-hand side, it's much simpler. And the person where you're trying to go is this little square here. So that shows there's a door here, you can just go inside the door. So this one just shows the relevant information, much less cluttered, and this shows everything as well. So this is an example of doing the information filtering, like I showed here. So if you're building a wearable interface, you have to think about how you'll be able to present information and filter information. An important element of wearable computing also is being able to show text. So in general, text does not really fit very well on screens, and you've got to think about with Google Glass, when you show text on the screen, you'll have some background as well, like in the real world. So how can you show text best on the background to make it so it's easily to read? So this was an example of testing out different types of text on different types of background. So you have some green text here, and the green text, of course, is very difficult to read against the green leaves. So you want to try and use some sort of billboard style, so wherever you're looking, the text is always facing you. You can also provide screen space annotation. So here is the view through the mobile AI application, and they are each of these bubbles here is a piece of information about an apartment that is for rent. So when you look at each one, then they pop up more information about the apartment, but they put this information on the screen, so it's screen annotated. One of the other challenges maybe is, how do you display information to assist you with navigation to points of interest. So here they're showing different ways of doing that. There's a virtual arrow appears on the ground, kind of radar display, and 3D arrow there as well. One solution people have done is you will use multiple different types of views. So you might have a map view for long distance navigation, an AR view for nearby navigation, and a radar view as well. With the Google Glass, you have quite limited field of view, so only 15 degrees. So there might be information that is outside your field of view. So the question is, how do you then show where that information is? So this is an example of that. This is a person, so here's the person's nose here, and you can see this is what the person can see. And these are the points of interest around them from the top down in the real world. So inside their view, there is maybe 1, 2, 3, 4 points of interest. But outside their view, there are all these ones here. So the question is, how do you show them what is available outside their point of view? And one way that can be done is through transitioning between views. So this is an application that was developed in Austria at the Graz University, and they were looking at how you could transition between egocentric and exocentric views. So the exocentric is a top-down view, map view. Egocentric is first-person view. So here's a top-down view here, and then you can then smoothly change into the first-person view, and then you see points of interest here. Or you can do it the other way, and you can move around, make the panorama as well. There's a video of this one. Let me just, actually, I think I have to find it on YouTube. Let's see here. Not this one. Let me see if I can find the person's name. Here we go. So what you see here is the person going outdoors and using AR browser. So they're looking around on the left side and they're seeing on the phone different tags appearing in the real world. So this is called context compass, what they're showing here. They have on top a little window showing all the compasses. Just go back again. And then on the bottom here they have a radar display showing where information is. So you can look around. But what they've been doing is being able to transition between exocentric and egocentric. So here's a map view, here's a panorama view. So you'll see that they can zoom in, so you can have zooming panorama. So you just hit the button and now it zooms out, and now as I look around, it keeps on combining, and I can push my button and it zooms in again as well. Here's zooming map, so you can move the map down, and it move the phone down and it zooms automatically to the map gesture, move up again, it zooms back into the first person view. So it becomes a very natural way of zooming in and out. So that's one way that you can show information that's out of your field of view. And the other way they showed it is by using the context compass. So the top, there's a bar, and then on top bar they had all the points just listed as points, and you could zoom around as well. So I wanted to speak a little bit now about cognitive models for wearable interfaces. So when you are moving around in the real world, then what people try and do is they try and split their attention between, if I'm walking around with my mobile phone, like the woman I was following yesterday was texting. She was texting on the phone, looking at the screen, but then at the same time she had to look up every so often and make sure she did not run into the other person or whatever. So so when you're having a mobile task like this one on the phone, it is competing with cognitive resources for other tasks as well. So at the same time she's texting, she's trying to, in her mind, make sure she does not hit anybody else, or she's thinking about where she's going. So when you're designing a wearable application, you have to think about people will be doing the same thing with your application. They might be looking at your application, but they're competing with other tasks as well. So one of the challenges is how do you design your application, or how do you know how much mental ability people are using? So there's a framework called the Resource Competition Framework that helps you do this. So this is a way that you can analyze the amount of mental cognitive ability taken to perform a particular task. And it's a resource approach to attention. So first of all, they make some assumptions. So they make 4 key assumptions. So one assumption is that your cognitive system is divided into separate modules. So in your brain, you may have one module that is responsible for processing language. You may have another module that's responsible for spatial awareness. Another module that's responsible for path planning. So when I'm going from my home to my university, then the path planning module will tell me which route to go. So in your mind, you have all these separate modules that are working, and the assumption is that they work in parallel, they work independently. So at the same time as I'm path planning, I can also be processing audio information or text information. But each of these modules have a limited capacity, so I can only do so much. And there is some sort of central control module that controls what's going on. So you may have cognitive interference happening where you've got two or more tasks competing for the same resources. So, for example, if you are reading, this uses your text comprehension module, but at the same time, if you are doing an addition task, then this will also use the same module, so they will compete with each other. So you can have cases, or if you are trying to listen to music, and at the same time you are trying to process other audio cues, and you have competition. So so there's a interference with between each module, and also the central processing that has to assign tasks to different modules can be overwhelmed if there's lots of tasks happening. So from a psychology perspective, you can look at what resources are needed for to perform different tasks. So for example, if you're walking, then you might need some motor control, so using your hands or legs, and then you need different resources. So you need some way to manipulate physical objects or position the person, sequencing, timing, control. If you are doing some attention, you're trying to get someone's attention using visual or auditory cues, then you need to be able to do some searching or selection as well. So the way you use this resource composition framework is you try and map the cognitive faculty to the task and look for areas where you have conflicts or overloads, and then these areas might be places where you can use technology to help improve that. So let me give you a simple example. If you are going to work, you might be doing different things when you go to work. So one is you can be walking down the street, so crowded street here. Then you might be riding on the escalator. You might, on the way to work, have stop and have coffee with some friend. And also, here you are at work now, that you, in this case, a woman is working in the lab, so she's lab technician. So which one of these do you think would take the most cognitive resources? Does anybody have any idea? Lab one?
Right.
Yep. Okay. That's not quite right. So does anybody have any other ideas? Yeah, it's the walking crowd. So if you look at what you're doing, so what you can do is, each of these require different tasks. So if we go to here, so there's, so here's some mobility tasks, here's some HCI tasks. So you can make a list of all the tasks that you might perform, and then you can see which tasks are required in different situations. So if you're hurrying through the street here, then you can look on the list here. You have to do walking, you have to do wayfinding, you have to do route planning, you have to do collision avoidance, and also some estimated time to target. So you might have to do these 5 things at the same time. If you're in the laboratory, then you just have to kind of control your personal space. Maybe you might do some typing, maybe one thing, but generally in the lab you're doing one thing at a time. Whereas walking, you're doing 5 or 6 things at the same time. So this one is very stressful and takes a lot of cognitive ability. Similarly, if you're having coffee in the cafe, then you're doing some talking, some waiting, maybe sidestepping, getting away people, controlling personal space. But only 4 things, not 5 like this one. So then you can say, okay, well, the person is doing 5 things here. What can I do to make it less stressful for them? So if you think about the wearable computer, and you think about these 5 things, walking, wayfinding, path planning, avoiding collisions, time to target, what could we do with the wearable computer to make this less stressful? Right. Mm-hmm. Yeah, so that's right. So Cornell says you can use augmented reality to show the path. So if we go, in this case, here, so if you have the augmented reality and you have an arrow pointing where you should go, that means no longer do you have to do the path planning because it tells you all the time. So now instead of having 5 things to do, now you only have 4 things to do. Also, you could also use the augmented reality to help with collision avoidance. So this picture here shows that one here. So there's it shows where people are around you, and so you don't hit them anymore. So now you can reduce that one. So my friend before, or yesterday, who was walking with looking at the phone and going to be hitting people, if she has augmented reality with Google Glass, then she can be texting, and before she hits, there'll be some warning saying stop, and she want to hit them. So now that gets rid of that one as well. So this is an opportunity, shows you how you can think of what the person is doing with all the tasks, and then think about which parts of the technology can be improved. So probably the wearable computer can probably not help with walking, so you always have to be walking, but it can probably help with the wayfinding and the route planning, the avoiding collisions, and also time to target. So when, with the, on your phone, if you use the maps, oftentimes it will tell you how long it takes to drive to location. But you have the same thing on Google Glass. You can start walking and it will say, oh, it's going to take you 15 minutes to get to location. So now I don't have to try and guess anymore. It tells me exactly. And the person on the other side, I can let them know and so as well. So this resource competition framework is a way that you can try and estimate how much cognitive tasks or requires of people, and then how to improve that with the technology. You can see here, for example, here is the Google Glass view, and it's showing you the map to a location, and it's showing you also the time as well. So it now gets rid of two of those things, the path planning and the time to target. So far we've talked about mental use of interfaces, but now I want to talk about physical applications, so the ergonomics. So if you're building wearable systems, then there becomes a question about where do you want to put the technology. And with Google Glass, it's all on the head, but there are other devices as well you can use. So I showed also some input devices where you can be touching your arm or your skin and having things here. So there was an interesting study done to say where you can place technology so it is unobtrusive. So they asked people where they wanted to put different types of technology, and they identified these particular areas. So on the head, around the neck, forearm, shin or foot, or around the waist here for carrying some weight. There's a study also done on where to place a trackpad, and they asked people, 25 different people, where to put a trackpad for user input, and most people preferred onto the thigh here, or on the upper arm here, or torso as well. Sorry, the thigh was preferred, but the upper arm was one of the worst places. And then people said, well, where do users want to use wearables? And so they had some percentage of people giving some feedback. So about 30% of people said they want to put it onto the clothing or on the wrist, and about only 12% said glasses, so quite a small percent on the head there. So when you're trying to design how to use wearables, you can think of it from an ergonomic perspective, from human system design. So you have to think about who is the user, what is their age, and then gender and what abilities they have. And based on that, what type of interface do you want to provide? So is it going to be using orientation, body posture? Then where do you provide that tool to capture that? Then what type of display do you want input device to have? And then the task as well. So these all feed together into designing the wearable computer. So it's both based on the form factor and on the task you want to perform, and that all drives the physical design here as well. One of the important challenges with Google Glass and other wearable systems is social perception. So when Glass came out, people started making fun of Google Glass, and I've got a video I can show of this one here. Let me just see on Saturday Night Live. Here's the video. This one here. And I won't show all the video, but I'll show some.
This suit's loaded with features and powered by the legendary.
Saturday Night Live, the sketch comedy show, did a bit
Not this one.
ridiculing.
Sorry. Yeah, I think it's this one here, actually. Yep. No, not this one either. Sorry. Okay, I think I have it on my hard drive actually. So let me pull up from the hard drive. Here we go.
Early versions of the highly anticipated Google Glass began shipping recently to tech bloggers. Here to give us his take on the new product, our Weekend Update tech correspondent, Randall Meeks.
So here's fake glass here, but he shows how it's working.
Thank you so much for coming. So tell us, what are your early thoughts?
Oh, Seth, they're amazing. I used to spend so much time in my life looking down at my phone, and now thanks to Google Glass, the phone is up here. I can use it without being rude or distracting. and it's simple. You just toggle through the menu like this. You have to activate it kind of this. Like this. Almost there.
Yeah, that's pretty cool.
It's great because no one knows you're doing it. Come on.
I mean, I noticed you're doing it.
Oh, sure, because it's there we go. It's on. Okay. Now to give it a command, all you have to do is say "OK Glass." Okay. Now, what's your Wi-Fi password?
Oh, at NBC, it's Peacock.
Peacock. Peacock. Password Peacock. 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 Password Peacock. Isn't this great, Seth? And now, if I was doing this on a phone, I wouldn't be able to talk to you like this while I was doing it. Peacock. 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 And I'm on? No, I'm not. Okay, go back. Go back. Here we go. Here we go. Here we go. One more. Almost there. Go back a little more. It's that easy. Best of all, they look like totally normal glass.
Oh, I don't think that's true.
Seth, these glasses can do anything. Okay, for instance, are you hungry?
Sure.
Yeah, great. Me too. You want to order some food?
Yeah.
What do you want?
I don't know. How about Italian?
Yeah, I like Italian too. Okay, glass. Italian. 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 Oh, no, just change the language. Italian. Occhiali. La tomatia. La tomatia. Inglese. Now we're back. How simple that was.
I gotta say, glass doesn't seem at all that
Well,
convenient.
just don't talk about like doing this.
Wait, you mean
No,
if
don't
I
at the
talk
same time as
around
the
the
glass.
glasses, I'll
Don't
confuse
no.
Wait, are you watching porn on your glasses?
Mute. 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 Okay, glass. Mute. There you go. Good. Ow. Reboot. Reboot.
So anyway, so it's a bit funny, but you can see there's still some as you've been using glass yourself, there's a lot of social perception and issues as well. So when you're building interfaces, you have to think about how you'll be perceived to other people. For example, there was this company called TAT, and they decided that they would build a mobile application that allows you to scan people's faces. And when you hold the phone up, it scans your face, and then there's face recognition, and then around your head, it will put some information about your social networks. So you see the LinkedIn or Twitter icon, and I can tap on the icon, and it provides the profile. So that seems like a very nice application, because you can go to a party and you can hold your phone up, see somebody, and then you can see and you can tap around their place. But if you think about how you use it in business setting, so I'm going to a business meeting, and the first thing I do in the meeting is I sit down and pull my phone out and I go around like this on the meeting. Then it changes the dynamic. So somebody said, well, if that was happening to me, then it would be like being stopped by the police for ID, or something like security scanned, or being like, show me your papers. And one person said that anybody trying to point a device in my direction better be prepared for a lawsuit or a punch in the face. So there's some social issues around glass as well, and that means that for, at least in my opinion, Google Glass is very well suited for professional or business applications, niche applications, but there may be some way to go before it is used by a general consumer. Because if you start bringing it into the public space, people start worrying, are you filming me, or what are you seeing on your display? And already there's been some examples of people who have been wearing glass into the pub or the restaurant, have been told to take off, or there's one woman was beaten up because she had the glass on. But if you think about using it in a professional setting, like for military or police or medical, where people are already wearing uniform or some, having some devices, then this might be very, very suitable. I've talked about hardware prototyping already, so let me skip through this one. Yeah, and I talked about this one as well. Okay, so what I wanted to do lastly to finish is talk about some research with Google Glass or with wearables as well, some research directions. So let me just go back to the other set of slides. And okay. All right. So I think with wearable computers there's a lot of different research challenges and directions, and I guess, well, you four are from university, you're from companies, so, but from a university perspective the research is very interesting because that's where you can make the publications, and when you're starting your lab, this could be where you're going to be getting the research outputs. So about 10 years ago, Dad Starner wrote a article called The Challenges of Wearable Computing. And this article he gave a list of some of the key challenges of wearable computing. So one is privacy, low power, networking, collaboration, heat dissipation, designing interfaces, building tools that can help enhance your intellectual ability, and also augmented reality systems. So in many cases these challenges are still the key challenges today. So if you're using Google Glass, if you run the camera the whole time, then the glass will run out of power in about 45 minutes or 1 hour. So it does not provide a wearable experience for the whole day. The privacy issues are still a big privacy issue when you are looking around in the real world. So let me give you some examples of research being done in different areas. So for interface design, there's been a lot of research being done now on gesture-based interaction. And I think yesterday you would have seen demonstration of what we've been doing here in the lab. So it's I showed you the video before of very simple gesture interaction with glass, where you can be doing swiping or tracking hand position. What we're interested in doing is tracking the 3D position of hands with glass as well. And so what we do is we kind of cheat. So we use the 3-gear system, and this uses the Kinect to be able to capture hand position, and then you can capture the hand position and the hand shape, and then you can send this wirelessly over to glass. So I think yesterday you saw the demonstration from Hudong where you could sit down. Did he show you this one? And use your hand gestures to interact with glass or with other areas as well. So he is interacting here, and then we built an augmented reality application where you can be touching objects in the real world and use full 3D hand model input. And this one will work about 15 frames per second, about 1 centimeter resolution accuracy. And we did some user study to see how does input with this compare to input using touchpad for positioning objects or combined input. And we found that glasses about using the gestures was about 3 times faster to position an object rather than using touchpad to move it around. Another company which is doing similar work is the Meta. And Meta is doing work with what they call space glasses for depth sensing. So let me show you the video from what they have. So let me just pause a second. So what you'll see, this is concept video. So not everything on the video here is real, but it shows you how they imagine that it will be used in the future. And they're using see-through display, so it's a little bit like the Epson display. So it's quite bulky right now, but you put a display on, you can see there's a chessboard, and they can move their finger to move objects. Now she's sculpting the vase with her finger, and she can put things on here. And when it's finished, you can put it onto a 3D printer, and the printer will then start printing the vase as well. Now he's meeting some people, and this is kind of like I showed before with the face recognition showing what people's like. They have started now to make some pre-orders for some, but the system is still not working completely perfectly. But I will show you. So this is what the glasses look like, and then the goal is to make a 3D display appears in the real world that you can use your hand gestures to interact with as well. Great. So that shows you what people are doing with gesture interaction. Another area for research is collaboration. So okay. So for example, what we're interested in HitLab here is social panoramas. So the idea is that with wearable computer like glass, you can have ego vision based collaboration. So you have a camera on the head, so you could stream the camera video to a remote person, and they can see what you're seeing. And because you have the camera processing, display, and connectivity. However, there is some limitations with that one. So with Google Glass, you can do first-person remote conferencing, Google Hangout, but some of the limitations is it's just a single point of view, and you can only look where the person's looking because you have to look with their camera. There's also no spatial cues before, and there's no ability to annotate or to draw on the application. So what we're interested in here in the HitLab is how we can move beyond those limitations, and how we can capture and share social spaces in real time. So the idea is you could go to a location with Google Glass, you could pan around, you could then capture some surround panorama, and then send that to a remote person and enable the remote person to feel like they're really with you in space. And you could also have shared annotations as well. So we have built a little prototype of this one. So we take Google Glass and we look at the panorama, share the panorama to the remote person. The remote person can see the panorama on tablet or desktop, and they can annotate as well. When you do this, though, there's some interesting research questions. So one question is if both people can look at different parts now. So I'm looking at one piece of the real world, my partner's looking somewhere else. Then the one question is knowing where the partner is looking. So in order to do that, we've looked at doing things like having enhanced radar display. So this red wedge here shows where, the top-down view shows where I'm looking. This shows where my partner's looking. Or you have this context compass here where this is the view that I'm looking at, this is where my partner's looking. Well, the other piece of interesting piece is interaction. So now when you've got two people looking at different places, then how can you do the shared pointers or shared drawing? So let me show you a video of this working, and you can see what it's like. Here we go. So here's one of my students, Caroline. She goes to a very nice part of Christchurch. And now she's trying to share that with her remote friend here. So as she looks around, you can see where she's looking there. And you can see, now we can use his finger on the tablet to move around. And she can see the pointer moving on her display. And now he can draw on his display saying, oh, you know, we'd like to put a bridge here. And then on her view, she can see the annotation appearing as well. So it's a way to have some shared experience that moves beyond what you just get with Google Glass. And we've done some user studies with this one as well. And what we found is that having visual cues really helps increase the remote awareness. People prefer to point rather than drawing. And if you've been using the glass touchpad very much, you'll know that drawing on glass itself is quite difficult, you know, to do accurately as well. But anyway, this is an example of the type of research you could do in the future on remote collaboration. The last area I want to mention is intellectual cues. So you can use the wearable computer to help you manage information in the real world and find out more information about the real world. So one of the projects I worked on a while ago was looking at context sensing and using the context to manage information around you. So you can take context from a number of locations, so from what people are speaking, what people, their gaze, what people are looking at, and also from their location in the real world as well. So we combine this together into a wearable AR display. In this case, we used a special system that was developed by Nokia that had a wearable computer, but it had an eye tracker in there as well. So they used holographic optical element here. So here's the display here. They can see here, but they added also a second camera here, and the camera would be able to track your eye position, so it knows what you're looking at. And we can now use this for gaze interaction. So we built an AR application. So here's the AR view here, and the idea is that when you meet somebody, it can give some information about their name, what they're doing, but if you look at them more, then it will give you more information as well. Or if you look at the poster that talks about their work, it gives you more information about what they're doing as well. So it looks at your gaze cues to try and infer what information you're looking at, and then provides you more information based on their context. It turns out that the people from WearScript, they also built their own eye tracker. So they made an open source eye tracker as well. So with the Google Glass, if you want to try to do the same thing, you could add a small camera on the bottom that will track your eye position. Let me show you the this one. So this is their eye tracking system. Here's the code available here, and I will show you it working.
This video, we're going to explore two new input methods for glass: a custom eye tracker and a device called a Makey that allows you to use everyday objects as input. To a large extent, input methods govern the context in which a device can be used, such as when standing in line at a crowded coffee shop, or for people with disabilities who can comfortably use it. By expanding the options available, we can make glass useful in more situations and by more people. Glass has three primary input methods: head gestures, speech.
Okay, class. Take a picture.
4K glass, share with Andrew Miller, and touch gestures. However, there are times when these aren't sufficient, such as when your hands are already in use, or when they're just cold. When you don't want to disturb the people around you by using voice input, or when touch gestures can be distracting, such as during a meeting or when driving. Eye tracking allows for accurately determining a user's gaze and their eye motion, which can be used as gestures. Eye input can enable intuitive item selection and interactions that are more subtle than touch gestures. To do this, we extend the People Project's webcam modifications, along with our custom 3D printed mount, to produce a $25 eye tracker for glass. We tear down a webcam and replace two surface-mounted blue LEDs with infrared LEDs to illuminate the user's pupil, and we place the modified webcam in our mount for glass. This model was printed by Formlabs on their high-resolution Form 1 3D printer. These are the only parts required if you'd like to build one yourself. Keep in mind that this is to enable eye tracking and accessibility research on wearables until they become standard with the device. We don't recommend walking around with it on. A common misconception is that glass already has eye tracking built in. There is a proximity sensor which is used for on-head detection and can be used for blink and wink gestures. However, it doesn't know where you are looking. Like our device, the proximity sensor emits an infrared light to sense what is in front of it. This is what the light looks like through our own IR-sensitive webcam. Before we jump into eye tracking, let's look at what we can get just by using the detected pupil radius along with the ambient light sensor on glass. We use the dimmer switch to vary the light in the room to observe the relationship between them. Here we plot the ambient light in red along with the pupil radius in green over time. This clearly produces the expected inverse correlation and is shifted since the pupil takes time to correct for the change. This is interesting because it could be used to determine when the pupil size does not match what we'd expect due to a variety of factors such as stress or intoxication. Now we develop a method for performing gestures using the eye tracker. We create zones on the screen and perform a calibration process where the user looks at dots on the display. We treat each zone as a Gaussian distribution and use the Mahalanobis distance to determine if the user is looking outbound. Next, we demonstrate a way to manipulate the glass timeline programmatically.
This is a browser window, and I have glass connected by USB with debugging turned on. Press Home to wake up the device. I can then navigate the menus to take a picture. I can also launch activities directly, such as Settings, Launchie, and the WearScript launcher. In the web keyboard for glass, I can also use my keyboard keys like left, right, and more. If you have rooted your glass, you can get slightly snappier performance on simulated touch events by pressing the root button. You can see that it worked by the root logo. Finally, I can connect wirelessly to the device. I now disconnect the USB cable, and I can still navigate and launch activities.
Now we combine the eye tracking with Scott's web keyboard for glass. Just by using eye gestures, I'm able to navigate the glass display and record a video. The plot shows two zones, with red points belonging to neither distribution. We developed a custom eye tracker based on the maximally stable extremal regions algorithm. The pupil region is colored red, and an ellipse is fit to it shown in green. The pupil center is denoted by a small green circle. This is a makey-makey.
So I'll stop this one. So you can see this is something, another topic, which you can see what they did was to make a custom eye tracker, and then you can use that for eye input for glass as well. It could be provide some very interesting eye gesture interaction. So that's everything I want to talk today about research directions. I also have some slides here that I'll put onto the web for different resources. So these slides here talk about different programming resources for Google Glass and books and other things as well. So before I go though, and Gunn will come and start talking to you about some of the other things, does anybody have any questions about, one last thing I forgot to mention too, is in terms of the one very important area of research is around some of the social implications we talked about before. And I want to show, just to as an example of that, a little bit of a very interesting video called Sight. So this is a concept video of what it might be like in the future. I'll just pause here. So this is a concept video of what it might be like in the future to have wearable display, but in this case it's a contact lens. So you can imagine that when the display goes from here into the eye, then it becomes very unobtrusive and you can use it in many, many situations. But this could also be have some unexpected results. So this, I'll just show a little bit of the video, and then if you like it, if you go onto Google or YouTube and look for Sight and augmented reality, you can find the rest of it. It's an 8-minute movie, but I won't show the whole movie. So what you see first of all is this person, and it's a little bit strange what he's doing. So he's kind of lying on the ground here, and rolling around the ground. But actually what he's doing is he's playing a game. So as he's rolling around, he's trying to fly through the thank you.
Good job. Excellent. Well done.
Okay, so now he's finished the game. Does exercise. And then by using the contact lens display, if you look in his eye, it's a little bit glinting. This is a display here. It can make kind of all of life a game. So he's going to go to the fridge, pick some food out, and he has the cucumber, and then he has this game called Chef Master, and Chef Master is for cutting the cucumber. So every time he cuts correctly, he gets some points. Pardon?
It's all gaming, right?
Yeah, that's right, yeah. Oh, he made a mistake, so now he has to start again, do another one. Now it's cooking, and it tells him where to put the egg. So he puts the egg there, and he gets some points for putting the egg place. I won't show you everything, but I'll just fast forward a little bit. And then what he's going to do is he's going to go on a date. But turns out he's not very good at dating with women, so he uses this to give him some help, to help him. But first of all, he's waiting for the woman. So while he's waiting, he's got this application that shows some stars, and he can do some stargazing. So he's waiting, looking at the different stars.
Patrick?
And there's his date.
Hi. Hi, Daphne. How are you? Sorry.
It's okay.
You look great.
Thank you.
Love your jacket.
Thanks. It's a sports jacket, so that's official then. But
What do you mean?
sorry.
What's the difference between sports jacket and a
So
normal?
now he's going to launch this application. The application is called Wingman, and it helps him in the date. And she has a hard score, so he says she's a difficult woman to date. And this is what she's doing. She's posting on Facebook saying she's had another bad date.
I hope you're hungry. This
Yeah.
place has the best burgers in town.
Oh, actually, I'm vegetarian.
Oh,
Yeah.
really? Because you didn't say it on your profile. So.
Well, I don't write everything on my profile.
No, she's saying, oh, so the Wingman is saying, oh, suggest go somewhere else.
No. Just find something on the menu.
Well,
And
how
now
about
saying,
that?
suggest a wine.
Yeah. Great.
Now he's got the...
So, are there any other things on your profile that you didn't write about that I should know, or?
Okay, I'll stop there, but you should watch the rest of the video. It's very interesting, and it kind of turns into a little bit horror story. So it shows how, in the future we might have some wearable glass displays in the contact lens, but it could also be a bad situation as well, and it could be some negative context as well. Yeah, so in this case, I'm not sure what they thought they use input. Maybe they use eye gaze. Maybe they have some thought patterns, or there could be a variety of input devices that we could be using. But yeah, that's right. Great. So that's everything I wanted to say with you this morning. Does anybody have any questions about what I've shown you? I said I'll put these slides up on the Google Drive, and so you can get access to them as well. No questions? So if not, I'll get Gunn and he'll come in and he'll talk a bit more about some programming work, and then you have some time to program, and then we'll come back after lunch and we'll see how you're doing. And about 4 o'clock, I would like each of you to make a small presentation about what you have been building or thinking about building with Google Glass as well. So if you have some prototype or some screens, you can show that. That will be fine. Yeah. Great. Also, I should mention that I think today. Now there are more food shops open on campus as well. So if you go underneath the library, they have now the I think the Greek food place, and also the noodle Chinese noodle is available, and also hamburgers as well. So because students are coming on campus on Monday, then they open up all the food shops. So if you want to try somewhere for lunch, you can go into the library there as well. Great. Well, I need to stop, and I'll go and get Gunn, and then I will see you a little bit later. Oh, no, I can use this. Great, so Gunn is just coming. Go another meeting. I'll be back after. Sure. Nice to keep more people. All right, sure.